After we have discussed this allowable bearing pressure of a foundation in sands and clays, let us take some illustrative examples. But before taking the illustrative examples, let us refresh our memory about the summary of the bearing capacity equations, mainly the general bearing capacity equations given by our code. So you remember that this is our equation for net ultimate bearing capacity, where the basic equation is CNC plus Q into NQ minus 1 into half gamma Bn gamma, and the shape, depth and inclination factors, and also the water table reduction factors are to be used depending on the profile, soil profile, and also depending on the depth of water table and the inclination of the load. And the values of bearing capacity factors given by our IS code are like this. These are already familiar to you, and these are the shape factors, values of shape factors. And if we have a strip putting, you remember that all these shape factors are 1 or unity, and these are our depth factors. But for conservative design, usually we do not use these depth factors, because unless the soil excavated for foundation construction is not filled back and properly compacted, the depth of foundation, increase of bearing capacity due to these depth factors should not be considered as a conservative design measure. And since in India we do not compact the filled back soil after the foundation construction, therefore usually it is safer not to use these depth factors. Alright, so now let us go for these illustrative examples. I have selected a few examples. The first problem first. So let us determine the ultimate bearing capacity. Determine the ultimate bearing capacity of a strip footing 1.5 meter wide at a depth of 1 meter, resting on a dry sand stratum. So it is a very basic kind of problem, and the values of dry density of soil is given, gamma d equal to 17 kilonewton per meter cube, and the effective angle of shearing resistance is 38 degree. So it's quite a strong soil, and because it is dry sand, cohesion is 0, and we are asked to use the bearing capacity factors as per IS 6403. Alright, so let us solve the problem now. So here I have drawn the strip footing. It has a width of 1.5 meter and a foundation depth or DF equal to 1 meter. Okay, and the given value of gamma is 17, phi is 38 degree, and therefore if I use the bearing capacity factors, if I use the equations, then I get n phi, which is tan square of 45 plus phi by 2. Using phi equal to 38 degree, we get this value as 4.2037. And using this n phi, the NC, NQ and N gamma can be obtained by using the appropriate formulae, which we have already seen. Let us once again see this. This is our N phi and NQ and NC and N gamma. So I have already obtained their values by using appropriate formulae, and they are NC is 61.3571. In fact, since the soil is cohesionless, this NC will never be used, and therefore I even don't need to calculate the value of NC. Okay, so I write a note that this is not needed. Here for this problem it is not needed. Okay, then comes NQ. And Q is 48.933, 48.933, and N gamma is 78.024. And therefore I can find out now the net ultimate bearing capacity, which is, you remember, Q and U is my C and C, SC, DC, IC. So that factor will not come because C is 0. Then Q into NQ minus 1 into SC DC IC into RWQ, water table correction factor, plus half gamma B N gamma into S gamma I gamma D gamma into R W gamma. The water table reduction factor, you remember that, let me draw an apple. So if this is above the foundation level, then this term, Q term, will be affected, and RWQ is given by, if you remember, 0.5 into 1 plus dW by dF, and it is not greater than 1. Okay, and similarly, if groundwater table is below the foundation depth but within a depth of B from the foundation level, then this term will be affected, RW gamma, and in that case my RW gamma will be, in fact, 0.5 times 1 plus depth of the water table from the foundation level. So I will call it dW minus dF in this case, because dW will be larger than dF by B, and that is again should not be greater than 1. Now in this problem, nothing has been mentioned about the groundwater table, So we'll assume that groundwater table is at a great depth, and therefore both these water table reduction factors will be just value will be 1. So we need not calculate them, and therefore by putting the appropriate values of Q will be how much? It is the surcharge, so gamma into dF, so 17 times 1 times NQ is how much? 48.933. so 48.933 minus 1, and since it is a strip footing, this will be 1, then shape factors will be 1, depth factors we will not consider, and since nothing is mentioned about the inclination of the load, we will assume a vertical load, and therefore inclination factor will also be 1. So all these factors will be just 1. So the first term will comprise only of this value, and the second term will be half times gamma is 17 times B is our 1.5 meter, then n gamma is how much? N gamma is 78.024. 78.024, and this will give me a value of 1809.667. 1809.667 kilopascal. Okay, and usually it will be rounded off to 1800. Okay, kilopascal, and therefore my net safe bearing capacity QNS, if I use a factor of safety of 3, then I will have 1800 divided by 3, so 600 kilopascal. Okay, and we assume here a factor of safety of 3 as usual. So this is my solution to our problem. I can box the results. And QNS is 600 kilopascal. So this completes the first problem. Okay, coming to the next problem. This is the problem. The same footing we are considering here. It is a strip footing of 1.5 meter width. The depth of foundation is 1 meter. And now the phi value is changed from 38 degree to 32 degree. And we are asked to find out the net safe bearing capacity using the general bearing capacity equation as per our IS code. Alright. Now I think you remember that okay, let us start with solution to example 2. I'm very sorry. Solution example 2. Now before we start solving, I think you remember that we have seen that there are three modes of shear failure below the footing: general shear failure, local shear failure, and punching shear failure. So when we have phi equal to 36 degree or more, greater than equal to 36 degree, then we have general shear failure condition, general shear failure. And when phi is less than equal to 29 degree, then local shear failure takes place. And in between we need to interpolate. In between we need to interpolate between general and local shear failure. This we discussed in the second lecture. Now you also remember that Terzaghi gave us the empirical method to handle this local shear failure condition, and he said that when local shear failure occurs, we should use a reduced phi value. We call it phi local, which is tan inverse of 2/3 of tan phi. Yes, and similarly we need to reduce the cohesion to C local, which is 2/3 of C. Alright. Now in our case the phi value is 32 degrees centigrade. 32 degree. Alright. Therefore it lies between 36 and 29, so we need to interpolate, and for that purpose we will have to find out the bearing capacity factors for phi equal to 29 degree but with a reduced phi. Okay, that will give me the bearing capacity factors for local condition, and I'll have to find out the bearing capacity factors for phi equal to 36 degree, because that is the limit where general shear failure, that is the minimum value of phi where general shear failure occurs. Therefore now if I put phi equal to 29 degree here in this equation, then I get phi local as 20.29 degree, and in our case there is no cohesion, so local C doesn't come into picture. Now what I will have to do, I will have to use phi equal to 20.29 degree to get the bearing capacity factors for phi equal to 29 degree in the equation. Okay, suppose I call them, say, NC29 and Q29 and N gamma 29. Okay, and if I find them, then I get their values as 15.11, 15.11. I'm very sorry, it is not 15.11, it is 15.11, and NQ I get 6.586, and gamma for this condition I get 5.61. Okay, you can put phi equal to 20.29 in the bearing capacity factors equations for bearing capacity factors, and then you will get these values. Okay, Similarly, I can use phi equal to 36 degree for the general shear failure condition, and then for phi equal to 36 degree I call these factors as NC36 and Q say 36 and N gamma 36, and these values are obtained from the bearing capacity factors equation, Indian standard equations, as 50.59. 50.59 is my NC for 36 degree, and Q for 36 degrees 37.75. 37.75. You need to calculate them putting in the formulae. I have already calculated and I am writing the values here, and N gamma 36 is 56.31. Okay, now I need to linearly interpolate for a value of phi equal to 32. Phi equal to 32. So what shall I do? I shall find out for phi equal to 32, for phi equal to 32, I will do the linear interpolation like this. Say I want to find out, I don't need NC in this case, so I will not calculate NC for 32. I will calculate say NQ 32. So NQ for my calculation of phi equal to 32 will be given by what? Will be given by I'll get the value as NQ29 plus what is the difference between NQ of 36 and NQ of 29? It is 37.75 minus NQ of 29 is 6.586. 6.586. This I should divide by 36 minus 29, which is 7 degree. Okay, 36 minus 29 into, now what is the difference of my phi from 29? It is 32 minus 29. So this will give me the linearly interpolated value of NQ for a phi of 32. So this I will get as 6.59 say plus whatever value it is. This comes out to be, let me calculate for you, 37.75 minus 6.59 is 31.16. 1.16, and this is 7 into this is 3, right? So I get this 31.16 divided by 7 into 3 plus 6.59, which is 19.94. 19.94. All right. So it is 19.94. In a similar manner, I can get n gamma for phi equal to 32 degree as n gamma 29, which is 5.61 plus, I'm very sorry, it's quite difficult to write here, not easy. And gamma is for 36 degree, it is 56.31 minus for 29 it is 5.61 divided by 7 into again 32 minus 29, and this will give me a value of 27.338. 27.346. All right. So these are my values of NQ and N gamma, which we have got by linearly interpolating. Remember this. Now I will use these values of NQ and N gamma for finding the net ultimate bearing capacity, and that I can do it pretty easily. So Q and U is my, it's a strip putting, and we will ignore the depth factors, so I will have Q and Q into NQ minus 1 plus half gamma B and gamma, right? And therefore Q is my searchers is my density was 17 kilonewton per meter cube into depth of foundation was 1 into now NQ minus 1 will be 19.94. This 19.94 minus 1 will give me 18.94, so I'll put this value directly, plus half into 17 into B was my 1.5 meter into N gamma. N gamma is 27.34, and this will give me a value of 670.54. 670.54 kilopascal. Okay, and therefore my net safe bearing capacity, if I use a factor of safety of 3, I will get 670.54 by 3 using a factor of safety of 3, and that will be how much? That will be 670.54 by 3, 223.51. 223.51. we will round it off to say 220. Actually I should round it off here itself, 670, and then 670 by 3 is 223 anyway, so we will further round it off to 220 kilopascal. Okay, because soil is a very uncertain material, and therefore we try to be always in the safe side, so we are rounding off at both the stages. Alright, so this is how the linear interpolation of bearing capacity factors for between general and local shear failure is done. Alright, so this completes our second problem. Okay, coming to the next problem. Find the net ultimate bearing capacity of the footing in the example 2, that is phi equal to 32 degree, if the groundwater table is at a depth of 0.5 meter below the ground level, and if the groundwater table is at a depth of 2 meter below the ground level, and we are asked to take the saturated unit weight as 20 kilonewton per meter cube. Okay, so now in this problem the effect of groundwater table has to be considered. We have two cases. Case A, when the groundwater table depth is 0.5 meter from the ground level, and when case B is when the groundwater table is at a depth of 2 meter from the ground surface. Okay, and the soil is same, therefore we will have to use the same values of NQ and N gamma, because the phi is same. We had already got the values of NQ and N gamma for the linearly interpolated value, for the case of phi equal to 32 degree. Okay, and these same values we are going to use in this case also. Only thing we need to do is we need to consider the groundwater water table reduction factors. Okay, so let us write down the bearing capacity equation now. So Q and U, we know that we have Q into NQ minus 1. Shape, inclination and depth factors are all equal to 1 for us. Now I have to consider the RWQ plus half gamma B and gamma into RW gamma. Now in this problem we are asked to use gamma saturated as 20 kilonewton per meter cube, but when we consider the effect of water on the gamma in terms of these water table reduction factors, these factors, then we need not consider the submerged density. Okay, so the original density we are going to use, because the effect of submerged density will be already taken care of by these factors. So Let us also write down the bearing capacity factors for phi equal to 32 degree. This is our solution for example 3. I forgot to write. Phi is my 32 degree, and we already had this value of NQ and N gamma. NQ was 19.94, and N gamma was 27.34. Now we need to find out the water reduction factors. So for case A, I have my water table at this value, this between ground level and the foundation level. So obviously RW gamma, which affects the soil below the foundation, that value will be obviously 0.5. Okay, and since the groundwater table is not at the surface, therefore RWQ will not be 0.5, but it will have to be obtained from the formula. Okay, so for this case I know that RWQ will be how much? 0.5 times 1 plus depth of groundwater table. Depth of groundwater table is 0.5 by DF. DF is 1. Okay, but not greater than 1. So it will be 0.5 into 1 plus 0.5. So 0.5 into 1.5, which is 0.75. So RWQ will be 0.75, and RW gamma will of course be 0.5, because the whole soil below the footing is saturated, okay, below the groundwater table. Therefore my QNU will be how much? It will be 17 into 1 gamma into DF into NQ minus 1, which is 18.94, into RWQ, which is 0.75, plus half into gamma. Gamma is 17 into B. B is 1.5 into N gamma. N gamma is 27.34, and this will give me a value of 415.7. 415.7. Say it is 415 kilopascal, and therefore Q net safe bearing capacity will be this value divided by factor of safety. So 415 by 3, this will be how much? 100 plus 100 by 3 is 33, so 133 plus 5, so 138. 138. Okay, so if you compare this result with the earlier result, our earlier result, was how much? What was the value of net shape bearing capacity? It was 220. Now you can see that it has decreased. Now from 220 it has decreased to 138, the shape bearing capacity. Okay, so this is how the water table affects our bearing capacity. Okay, so these are my results for case A. Similarly for case B, case B, what will be my value of RWQ? RWQ will be 1 because groundwater table is not within the depth of foundation. So RWQ is 1. That means the density within the depth of foundation is not going to be affected. Similarly, what will be my RW gamma now? RW gamma will be 0.5 into 1 plus, now depth of water table from the foundation base of foundation, and that is equal to how much? It is 2 minus 1. Okay, 2 minus 1, so it is 1 meter by B. B is 1.5. okay, not greater than 1, and this becomes equal to 0.5 this becomes equal to 0.833. 0.833. okay, and therefore my Q and U will be, the first term will remain same, 17 into 1 into 18.94 into RWQ, which is 1, plus half gamma, which is 17, gamma B is 1.5, gamma B, and gamma is 27.34 into my RW gamma, which is 0.833, and this gives me a value of 612.33. say 612. okay, and therefore my Q net shape bearing capacity QNS will be 612 divided by 3, 612 divided by 3, which is 204. Right? So now you see as we have lowered the groundwater table, the bearing capacity has increased from 138 to 204 safe bearing capacity, and similarly net ultimate bearing capacity has increased from 415 to 612. That's why dewatering always improves the bearing capacity, and when the groundwater table rises, the bearing capacity decreases. All right, so that's what we have learned now. You can see how the bearing capacity has changed. When there was water table was at a great depth, the safe bearing capacity was 220. When the water table is at a depth of 2 meter, it is 204, and when the water table is at 5.5 meter depth from the ground level, then it has become 138. All right, so that's how we can take into account the effect of groundwater table. So this completes our problem 3. All right.